Hello.
Hello, Wayne.
Hello, Tamo. It's good to see you.
Yeah, good to see you too.
Okay,
So where are you? You in the US or in China?
I'm right now in China.
Oh,
Yeah, so I'm visiting my family here.
oh, that's nice.
Yeah, I came back in early June. So last thing is I don't need to teach next semester, so I can go back in
Nice,
September.
nice. I need to teach next Tuesday. I'm getting too old for that.
Yeah, and I went to the Yellow River Basin.
Yeah,
In Inner Mongolia, in the
yeah.
Hetao Irrigation District. Have you been there
Yes.
before?
I'm not sure of that one. I have seen one of these things full of sunflowers because the soil is salinated. Yeah. Yeah, I don't know
Right.
that
Yeah, I
one, but
think
I've
that.
seen systems in the Yellow River. Yes, that irrigation.
Yeah, I think that one is probably the biggest irrigation system along the Yellow River.
Yeah, I might have seen it, but
China actually has a
I
field
don't.
station there.
Actually, we have written a paper with a student about that too, about the soil physics of it and how to predict the water table.
Yeah, I think it would be very interesting to look some problem there, because like you said, the soil salinity is a challenge there.
Yeah, the only way is but I will propose that they desalinate the water, that they pump the water, desalinate it, and then use it in the North China Plain. But how about that? The only way of doing something is to get the groundwater table down, right?
Yeah, I'm very much looking forward to your talk today. It seems interesting because it seems a simple soil physics message should be learned by a lot of engineers and folks
no
who are dealing
equations.
water problems.
No differential equations, no.
So almost start.
Yeah.
Yeah, I'm Cheng from Nanjing University. Nice to meet you.
Nice to see you.
Sure. Yeah, I'm a good
Thank
friend
you.
of Wei. Yeah. So he invited you. Thank you very much for the support.
Thank you.
Sure.
Yeah, Chen did his postdoc at Michigan State.
Yes.
I know well, yes. We know each other well.
Yeah.
How do I do this? I mean, can I show the PowerPoint and then talk? But how do I do that? Share the screen?
Yeah, the share screen. I think people should. I'm not sure. Oh yeah, you can share screen now.
Okay. Yes, I can. Okay, I can.
You have the Chinese painting on your wall.
Yeah.
Chinese.
You guys always give something, so I take those things up.
Sure. Great. Yeah, maybe time is coming, so maybe you can start. So before we start the EEH talk series, I would like to just a brief introduction to this speaker, Professor Thomas Steenhuis, internationally recognized hydrologist with research contributions in the United States, Sub-Saharan Africa, East Asia, and the South. And his early work was on the preferential movement of water and pesticide through soils and establishing guidelines for best management practices to protect surface drinking water supplies. His current research is on sustainable and water management to reduce land point source pollution and combat land degradation in developing countries. Professor Steenhuis has published over 250 peer-reviewed journal papers with H index over 70. And he has also advised over 150 graduate students in his 45-year tenure at Cornell University. Thank you. So you can start now.
Okay, I have a question. At my screen, there is something. There is the doesn't look good. How does it look good to you?
I think it's fine. Looks, yeah, for
You
for
don't
me.
see mute and things like that. Okay.
No, it's okay.
So I will be talking about the. Actually, I will not show any equations, and I will talk about management practices and with examples in both in humid Ethiopian highlands and in China. So the challenge for agriculture is that we need to produce more food in the next 35 years, or actually not only the next 35 years, but many more because the population is increasing. But food production is ultimately dependent on the ecosystem services. So it is essentially that these are maintained. And there are many ways that people try to maintain those systems. But sustainable intensification is a new word, but that is what is being tried. And we can learn from the past whether it is feasible to maintain ecosystem services with best management practices. There's always lots of proposals out how to improve the agriculture, but not always they work out. And there are many, many failures. So we can test what will work and can see what needs to be done to get them working. So I will tell you first the conclusions, and then I will tell you at the end again. How sustainable intensification is possible, but it will require a thorough understanding of the hydraulical system. And in order to do it, it will need political will. That is actually the most important one. And it will not come cheap. It will either cost yield or taxpayers, or it will cost the taxpayers by investing a lots of money in these systems. So two examples, two case studies, one in the where I have worked in the semi-humid Ethiopian highlands, where all the time new land is developed. This is a system where there's more than 1,200 millimeters of rainfall, and it falls in 4 months. So it really rains. And then I also will talk about the North China Plain. You guys know more about it than I, so you can correct me on this, but essentially, there was a second crop introduced with groundwater irrigation, because one crop, you can only grow one crop with the 500 millimeters approximately that falls. So let's first talk about Ethiopia, the Ethiopian highlands. And you can see here where it is located. And if you look a little bit below, you can see that in the the only place in the Nile Basin is Ethiopia with some rain. It produces 85% of all water in Egypt and Sudan. And so it is not only important for Ethiopia, but also for the whole Nile Basin. And I think an amount of approximately 400 million people depend on the water from these highlands. So here you have an example of the landscape. This is where agriculture is done. It is also much more rugged in other parts. But in these parts, agriculture can be done. And this is during the dry season, shortly after the wet season, actually. So, and then there was a severe drought in the 1980s. And if you're old enough, you remember that was all over the news. And as a response, they attributed that the severity to a land degradation. And they started, and they decided that infiltration needed to be increased. And they invested in management practices. And at the site here, you can see one of these things, infiltration. Actually, they infiltrated the water, and on top you can see another example of what they installed. However, the problem of the drought was in the dry region. The sustainable intensification is different in humid and in semi-arid highlands, and I will show that next. What you see here is the landscape in a semi-arid area, and what you find the crops in the bottomland, you find the forest in the middle land, and so in these semi-arid areas, evaporation is greater than rainfall during the monsoon rain phase. So you try to get all the water, and you go to crop where the water is. That is in the bottom part of the valley. You have here a subhumid watershed, and if you look at the subhumid watershed, you find tree and shrubs on the steep slopes. You find crops on the intermediate slopes. You find grass on the lower slopes. And in these cases, the evaporation is less than the rainfall, so water will come down, saturate the bottom part, and you cannot grow any crops. So in these landscapes, the problem is not shortage of water, but the problem is excess of water. They apply the same management practices to both landscapes, and you might already understand that gives some problems. So we will be talking about the humid regions. A little bit about hydrology to get everybody on the same page. We have done many infiltration experiments, and you see here that Christian Guzman doing an infiltration experiment. And if you look at the infiltration experiment, if you plot, this is the rainfall intensity curve for that area. The probability of exceedance, the amount of the infiltration. And if you then look to the infiltration rate, you see that this is the minimum infiltration rate. And there is the medium infiltration rate. And in order to get runoff where the Hortonian flow, rainfall intensity must exceed the soil infiltration rate. And you can see there's little chance in the Ethiopian highlands that water will run off due to infiltration excess. Maybe in some lower spots where there's less infiltration, but that's only a very small part and only a very small set of the storms. And moreover, that will infiltrate down in the hill. So runoff is produced by saturation excess in these bottomlands. And that is really important, and that is important for these management practices too. So if you look at the landscape, you get infiltration first. Interflow, when the soil becomes, when these hillsides become at full capacity or saturation, interflow starts, flows to the bottom, saturates the bottomland. And once these bottomlands are saturated, you get overland flow by both interflow and by surface runoff. Also, there is some runoff from the degraded lands. If you look to the Ethiopian, and if you look to the various places, this is and the tit, the erosion rate is 5.2 tons per hectare per year. No gullies. This is Maybar, 7.4 tons, no gullies. This is Meswa, 10 tons per hectare, no gullies. Then you get Anjeni, that has one big gully, that has 25 tons per hectare. And Dewi Maui, I cannot read that, has a gully too. And then at the end of the Blue Nile, you get 7 tons per hectare per year. So there's lots and lots of erosion in these watersheds, only at the outlet, 7 tons per hectare per year. So not everything reach it, but still there's a lot of sediment. As I said already, talked about the reason is the gullies, and you see here some examples of these gullies. They are enormous, they are in the bottomlands, and we will discuss, they are extremely important to understand the hydrology. They are the main source of sediment. These gullies, you can find them everywhere. I found a picture of China. This is in the Guangzhou part. It is probably drier, but you can both see. You can see the grass here. You can see the grass here. They are both in the flat in the valley bottom. So this is the end of the lecture. And now we're going to use our knowledge in evaluating management practices. You see here the Blue Nile. You see here the Blue Nile Falls. These are at the lake was pretty clean. 30 kilometers south of Lake Tana, you find the Blue Falls, beautiful falls. Where there's lots of water, but lots and lots of sediment during parts of the year. And you can see that here. And the question is, why in 30 kilometers you get this much sediment? We will be talking about the Demi-Marvi watershed, and that's located between Lake Tana and the Blue Nile Falls. And that will give us an answer why we get that much sediment in that short of a distance. It's a 9-year water study. There it goes. The area is approximately a kilometer squared. The rainfall is significant, over a meter in 4 months. It's warm, but not tropical. It's high up. It is 2,300 meters. And there are 4 nested watersheds, and we will present the results of the nested watersheds and at the outlet. The watersheds are labeled, nested watersheds are labeled W1, W2, W3, and W4, and the outlet is W5, and I will indicate that. And it was done over 9 years. And okay, here you see the watershed. There are black soils, fertile soils in the bottom, and better and more oxy soils on the hill slopes. Several changes occurred in the watershed over these 9 years. Government installed infiltration furrows in the beginning. Farmers planted eucalyptus trees because the price of wood is high, so they can make more money from planting forest eucalyptus trees. It is also an investment. They need money. And the road was upgraded to an asphalt road, and the road bordered the watershed. Here you see the infiltration ditch, the governmental sponsored infiltration ditches. You can see you can see me on the side, and here you can see after a while what happens. They're already filled up with sediment. And it was done a lot. This is the furrows before, and all these black lines are the furrows installed. So they were done a lot in this watershed. And you see another example of it. And the interesting thing is that these are the remnants of the government installed drainage furrows. They are locked up. And what you see over here is the local practice of farmers carrying off the excess water. They are just off the contour, and these farmers initiated furrows. Because they're just off the contour, they can carry off the water without causing erosions. Well, these other ones are on the contour and doesn't do anything to carry off the water. So eucalyptus trees were grown in that period, and you can see an example here of the many eucalyptus trees that were grown in these 10 years. And the small ones in 2010 are now the big trees. So let's see about what we found, what they found actually. You see the runoff coefficient at one side, and at the other side, here the dates. You see the rainfall really didn't change much, and above you see the different watersheds. So here you see the runoff coefficient of VO1. This is VO2, and that was affected by the road, so that is a little bit erratic because they built that one. This is VO3, VO4, and this one is at the outlet. And what you can see is that during the high rainfall years, the higher rainfall years, the runoff coefficient is greater at the outlet. In dry years, it is almost the same as the other or smaller. So what is happening is that during dry years, VS at the outlet during dry years, water infiltrates in the bottom valley land and then is transported out by faults. During wet years, it's so wet it cannot be transported out by the interflow, and you get surface runoff. Here you see the periodically saturated area in this watershed. And that's what I said, during dry years, water from the upland infiltrates. And during wet years, the rain that falls runs off. The sediment concentration is the same. You see here the sediment concentration in the axis. VO1, VO2 affected by the road, VO3, VO4, and this is at the outlet. And you can see at the outlet, the sediment concentration is much, much greater than any of these sub-watersheds which you can see over here. The sediment is being picked up after at least leaves the sub-watersheds. And why is that? This is because of you can find these gullies in these saturated bottomlands. And here's one example of them. And this is approximately, you can look at the trees, this is approximately 6 meters deep and approximately 20 meters wide. And the reason is, if you look at this graph, which is a little bit complicated, the blue line is where the water table is. If it is below zero, it is below the level of the bottom of the ditch. If it is above zero, which is over here, the water table is above the bottom of the ditch. All these bars indicate either the change in depth or the width. And you can see that when the water table is above the ditch bottom, so when there is saturation, that there is lots and lots of changes in the gully. So saturation causes these changes to occur. When there's saturation, the soil loses its strength and the banks slip. And once they slip into the bottom of the gully, water can carry it down. So it is not the flowing water, but it is first it is the failing of the bank and then carrying it out. You can see here the difference in sediment concentration. This is the inlet where the water is relatively clear, comes from the uplands. And this is downstream of that same in the gully, and you can see a high sediment concentration. So these gullies are really increase the sediment enormously. So this is an example of it. This is the time. This is the sediment concentration on the y-axis. The blue line is the input concentration in the gully. And like you see here, the red triangles is the output concentration. And you can see that the input concentration, especially at the end, increases 80-fold, or maybe 40-fold, in the beginning 3-fold. So these gullies really are important to understand, are an important part of the landscape. Farmers know this too, that they say at the bottom here the soil does not have the capacity to absorb the water. That means that it's saturated. At the top where we have red soils, there is no erosion. And the middle area is rocky with sandy soils, and this is highly eroded. At the bottom, the soil cannot take water up. So what about the infiltration furrows? I mean, what is there? Intended to increase in infiltration. But in the saturated areas, they will collect water. And you can see over here, and they can form a gully. And actually, these farmers were extremely angry about about this gully, because they said that was done by the researchers. And also, you can see that they also fill up with sediment in no time. So the spatial summary: the increase in sediment concentration is caused by the gullies in the bottom. Runoff occurs when the storage capacity in the watershed is filled up. Storage capacity depends on the amount of water evaporated in the dry phase. And now it looks to the temporary pattern. This was the spatial pattern I talked about. Okay, the colors are the same, but the meaning is different. The blue bar is the period, is the amount of runoff, in this case, before the installation of the soil and water conservation practices. The red bar is when the practices were installed, and the gray bar is after the practices were installed. You can see that the runoff, so the blue is early, the orange is in the middle period, and the gray is at the end. So you can see in all cases the runoff is decreasing in time. The sediment concentration is decreasing in time. Oh, that is over here. Also, the runoff coefficient is decreasing in time. And it is both in all watersheds, in the sub-watersheds, especially at the outlet, which is VF5. Why is this? If we plot the amount of water, so this system essentially, this is saturation excess, and the runoff occurs when the bottom parts get saturated. So what you see here is the cumulative effective rainfall plotted here, and this is the time. This is in 2010. There was only 200 millimeters of rain required to saturate the soil and get runoff. Shortly after, same amount, maybe a little bit more, but 200 millimeters. And at the end of the period, it required 500 millimeters of rain before you saw any runoff. So the decrease in runoff and the decrease of erosion is caused by the delay in producing runoff. And why is that? Runoff is generated by saturated areas, as I said before. They all need to be filled up before the rain occurs. Patches of eucalyptus trees evaporate twice the potential rate during the dry monsoon phase. There's the oasis effect. You have the same thing in China. These trees evaporate more than they would when they were standing in forest. Eucalyptus trees dry out the soil more than than native trees or fallow land during the long dry monsoon period, the dry monsoon phase. So therefore, it takes longer for the runoff to start after the dry phase. The soil needs to fill up by the rain, and there is less water in there, so it takes longer. So it is really infiltration furrows were not responsible because you could not see them anymore after the end. So eucalyptus trees are likely responsible for the decrease in runoff. We cannot say for sure, but it is very likely. Also, there are stories about that rivers dry up on eucalyptus trees. Farmers tell you that all the time. That is general knowledge. This is the scientific showing of it. And because there's less saturation, gully formation and soil loss decreases too, because there's less, the formation of gullies are less. So it needs to be repeated to make sure that it is true, but I'm pretty sure that it is. However, the problem is that not only the gullies stop, but also the springs dry up. And the reasons that the springs dry up, unlike before, there were many springs before they started the deforestation, is that due to soil degradation, the organic matter decreases, and then the fine soil leaches in, and you can see here a profile, the topsoil. And you see at the top 60 you see what you see below 60 centimeters is these big pores. These are the original big pores that existed before the deforestation. But in the topsoil, you cannot see any of these big spores, and they all filled up with sediment. So that is the reason that these springs dry up. The water cannot infiltrate anymore, and it will take a long time before the structure is established and these pores are connected again to the surface. And once they are connected to the surface, you will find that the springs will come back. Another solution is in order to feed the population is the Nile has a fall of, I think, 2,000 meters in Ethiopia, so it is ideal to build hydroelectric plants. It's very controversial with Egypt. But if you do that, you can generate money, and with that money, you can increase the standard of living, will reduce the birth rate, and less food is needed. But that is not hydrology, that is politics. Let's talk about the case study in China. Let me see what time I have. I don't know. It is completely different, as most of you know. The China plain is absolutely flat. And you can recognize here is where the North China, here is where the North China plain is. There's approximately 500 millimeters of rainfall, and it falls during the summer. Because the irrigation allows double cropping, only one crop was grown before. This is the unsaturated vadose zone. This is the groundwater, a well. And so this is the system. You get water out of the groundwater, irrigated, and that you can see over here. In order to understand the system, we need to, we can write all kinds of equations down, but before you do that, you need to understand the system. And once you understand the simple system, you can write the equations down, and that's probably the next thing to be done. So we simplify the system to soils to grow plants and groundwater, and we have a groundwater reservoir for irrigation. This is the simplified system. You have a topsoil, and this block, and I skip some dimensions because I want to do some calculation. It's 1 by 1 meter, and this, the bottom part is 1 by 1 meter too. So there's water being pumped by an irrigation hose in here, and water drips out. Any excess water will drip out back to the reservoir. And surface soil, the topsoil, you can see the comparison. This is the real system. This is the cupid flowers or cupid crops. And then you have the groundwater reservoir, what you see over here. And then in between that leaking, that has to go to the unsaturated FADO zone. And there is likely preferential flow to that FADO zone. We have looked at the groundwater table, and you can see excess rainfall years in approximately 1 or 2 years showing up in the groundwater 20 meters deep. And the only way of explaining that is preferential flow to the FADO zone. And actually, Sam Kung has shown that preferential flow is much more common than what we think in models as the RC flow. Anyway, so let's see. So this is our example. The evaporation is 5 millimeters per day. So for our box, that will be, if you do that calculation, and you all can, that will come out to 5 liters per day for 1 square meter. So we have several irrigation schedules, water saving technique, where we add 5 liters per day exactly. Efficient irrigation, where we add 7.5 liters per day, which is really good. This is normal irrigation, 10 liters per day, twice the amount of water that is needed. That is usually done, especially under surface irrigation. And inefficient irrigation, where we add 20 liters per day, that's an irrigation efficiency of 25%, which is not very good. And that looks to the real use of water. Water saving technique, we irrigate 5 liters. The evaporation is 5 liters. So the leaching is 0. So the net use is 5 liters. If we have our efficient irrigation, we apply 7.5. The use is 5. And leaching is 2.5. So the net use remains, of course, 5 liters per day. You can do that with normal irrigation too. You irrigate 10, evaporation 5, leaching 5. And then with the inefficient irrigation, still the use is 5, and the remainder is leached to the groundwater. In all cases, the net water use is the same, and the remainder is returned to the groundwater. So what this means is essentially that irrigation efficiency, and I will say that a few more times, will not affect the groundwater table decline. And that's what you can see in the plane 2. Was the revolution on the Mao when they applied lots and lots of water, and then science took over afterwards, and much less water was applied. And what we will see is that the groundwater declined at the same rate all the time. So, as I said, the groundwater use is independent of the irrigation on a daily basis for full-grown crops. You can argue on the margins that it makes a little bit different, but this is in general pretty true. So there was an experiment done by Carolyn Young, and we analyzed the experiments. And so 5 crop rotations were established on the 5 rotations: winter wheat, summer maize, peanuts, winter wheat, rye collection, sweet potatoes, with some other crops, and continuous cutting crops. And what was measured was the moisture content in the top 180 centimeters. And I think this was over 5 years, maybe 8 years, I don't remember exactly. And this is an example of the data collected. So you can see the moisture content, and this is for during the semester. You can see this is in the irrigation here, moisture content goes up, it dries out, and then there's here a smaller moisture content, maybe a rainfall. Here there is another irrigation event or a rainfall. And here there is some irrigation too, and then the soil dries out afterwards. So in order to analyze this data, we are interested in the depercolation. We are not interested in the moisture content, the moisture content per se, because it doesn't tell us anything. We want to know the system. So the root zone after irrigation, it gets about field capacity. The current delta S that is the change in moisture content in the root zone, and we can get that delta S data from this data over here, from the moisture content in this moisture content. We can look from 1 week to the next week, and we know what is delta S in the top 180 centimeters, the change in storage. And that is equal to the irrigation plus the precipitation minus the ET. We can measure the irrigation, we can measure the precipitation, and we know what the ET is too. It is at the potential rate, and we can, because the soil is pretty wet, approximately at the potential rate, and that should be equal to the deep percolation. So we can calculate the deep percolation if the soil is above field capacity by measuring the delta S. We know what the irrigation is, the precipitation, and the ET. If it doesn't get to above field capacity, the deep percolation is 0, and we recalculate delta S based on that. So it's a simple calculation, and it is, and you can see how accurate it is. And here you see the data. What you see on this axis is the percolation in millimeters per growing season, and you see here all these crop rotations. So you can see here, essentially we calculate a little percolation for these crops, which are winter wheat. And then you can see here too. And we see that there is a clear break at 400 millimeters. Here they are approximately 0, and then it decreases 1 to 1. And there's some scatter, but it is really not bad. It is, I mean, this is field data, different crops, and different duration. If we do it in millimeters per day, percolation millimeters per day, it tightens up. The same thing you see, 0, I mean, very little percolation over here. And then after 3 millimeters per day, you can see that there's a 1-to-1 line between daily precipitation plus irrigation and the percolation. So with this extension, you mean if you apply more than 3 millimeters per day, everything leaches, as in the example of the boxes that I showed before. So the net groundwater use of groundwater is equal to the evaporation by the crop minus the rainfall. That is the conclusion. I want to emphasize this, and that's what you see. Okay, you might not believe it, so we try to prove it. And here is the equation. The water table height is the water table height in the year before, plus F is the amount of crop grown. This is the North China Plains, so 90% of the area is in wheat and summer maize rotation, so we can assume that. Then you can see here, this is the precipitation minus the evaporation divided by the drainable porosity. And there's a 2 because there are 2 years involved. And based on these observations before, we think it takes 2 years for the precipitation to reach the groundwater table. And also we need then the evaporation over 2 years. And you see here the results of this simulation. Here, this is the water table, groundwater table below surface, and you can see the steady decline in time. These are 2 big rainfall years in 95, I think, or 96, 97, I don't know. And it took approximately 2 years for this water to reach the groundwater. This is, at that time, I think the rivers were even flowing. And this is the prediction based on this equation. So essentially, our calculation of this simple thing can predict the groundwater table decline. And it seems reasonable. It's based on the mass balance. So you can argue we should take 3 years or 2 years. The principle is this precipitation minus evaporation divided by the drainable porosity times the amount, the area grown with that crop. Again, this is kind of depends on the difference in the precipitation evaporation for well-irrigated field crop. If it is not well irrigated, the evaporation will decrease, but also the yield will decrease at the same time. And in stomata, so by closing the stomata, but also if you close the stomata, there's less photosynthesis too, so it decrease the yield. And it's independent of irrigation efficiency. In other words, the potential evaporation rate is more. If the potential evaporation is more than the rainfall, groundwater will decline. There is no way around it. If you grow more, if you evaporate more than what is the rain, then the water has to come from somewhere, and there's no other water in the plain than the groundwater, so that will decline. An example. So this is the root zone water balance. In both cases, you need 30 centimeters of water. That is approximately the deficit if you grow 2 crops. Irrigation is in one case 100. That's during the Mao years. The 30 centimeters current. The recharge in this case is 70, and 10 centimeters of recharge in the efficient case. The groundwater balance, you pump, in order to get irrigation, you need to pump 100 centimeters of water. Here you pump 40 centimeters, the recharge is 70, so the net loss in both cases is 30 centimeters. And you divide that by the drainable porosity, and you get the decline of 1 meter per year. You can, in order to do something about best management practices, what you can do is essentially grow 1 crop, and instead of evaporation of 76 centimeters, you get an evaporation of 40 centimeters per year. And if you look then to the groundwater balance, so you get the deficit is, there's no deficit anymore. But if this is 40 centimeters, you have a surplus of 6 centimeters, and that will increase the groundwater. So one way of increasing the groundwater is by not only growing 1 crop or 2 short duration crops. So if you can shorten the time that the crop is on the land, you will increase the groundwater. Or import water from elsewhere. So the management practices for sustainable intensification are growing less grain wheat will halt the decline of the groundwater. Import wheat from elsewhere. For each kilogram imported of wheat, you save 1 cubic meter of groundwater. That's probably not very popular. Imported water from the Yangtze River. You can see here the Yangtze River and the routes and if you import that water, there will be wastewater. And I think they plan 4 billion cubic meters of water from the Yangtze River by the south to north project. And you can calculate that stop the groundwater decline in an area of 125 by 125 kilometers if you use that wastewater. And of course, you can also decrease the evaporation by mulching, and the plastic mulching is very popular. And you can see over here. And however, the problem is that this plastic, you have lots and lots of plastic waste, but it will help the temperature and it will help water use, and groundwater will not decline as much. What about desalinization? Yes, that could be a solution. You need the ocean. In the Ray and I talked about the Yangtze River. There are many irrigation projects that have groundwater too close to the surface. And what you can do, I don't know about the price, you can pump that groundwater, desalinate it, and then use it for irrigation elsewhere. So that could be a possibility. Then you can you can have better production in these irrigation systems that are salinizing in the Yangtze River, and you can use that water if you can get it to the North China Plain, where the groundwater is short, or you can use it for bringing to the cities and then use the wastewater to irrigate, which is a practice that is being practiced. Okay, the conclusion is, with the right understanding of the hydrology, management practices for sustainable intensification can be developed and implemented that increase food production, decrease land degradation and erosion, but sometimes at great cost. Thank you.
All right, thank you very much. So, yeah, so now maybe some people can ask some questions. So, let's see. It's great. It's lots of information. Because I'm not, it's not my area, research area, but it's very interesting. And also, it's pretty much related to China, the situation in China, especially in the northern China.
I think you guys know this already, but.
So, Wei, do you have any question?
Yes, I do. Tamo, it's great to be your student again. So in that simple model, if we put more water, either through rainfall irrigation, there's some water that's going to go to recharge, like percolating downward, right? So
Yeah.
Here, I guess you assume that percolation never gets to the deep groundwater table, right? It's kind of lost somewhere, or it's kind of a.
No, it goes to the ground. It goes to the groundwater immediately.
Okay. And then,
So,
then I don't understand. Like if we put 100 centimeter water, the crop uses 30, and the evapotranspiration is 30. You have a 70 recharge. Will that water goes to the groundwater?
yeah, that's correct. But I mean, you pumped 100 centimeters of water out of the groundwater first.
Right.
If this water comes from outside the basin, then you gain. So if you get water from the Yangtze River, that is a gain. But the North China Plain is a closed system, so whatever. And the only loss out of the plain is the evaporation.
Right. Okay. Yeah. I think now I got it. So basically, we exchange the groundwater for the food we grow.
Yeah, that's right. And for the evaporation, you need, that is the additional crop. That water comes from the groundwater. You can grow one crop with the water of the rain. That the summer crop, you can grow that with the rain. And then the second crop, the second crop, the winter wheat, uses the groundwater in the North China Plain. If you go to the irrigation, it is opposite. You import all that water, and that gets the groundwater to the surface. So
right. Yeah, I think that's the problem in the Hetao irrigation system, irrigation district, because they import the Yellow River water for irrigation. So the problem there is the rise of the
groundwater. Yeah. So the only way is down there to pump the water out.
Have the soil. Yeah. Thank you.
Okay.
I really enjoy the way you simplify the system.
Yeah, that's that's needed before you can write the equation, right? And I think it will be extremely interesting to know more about the recharge, how fast it is, how it does occur, because it has to go 40 meters deep, and it is amazing that it only takes 2 years. But so
Yeah,
this whole, if you model it the traditional way, it never reaches the groundwater. The groundwater table declines faster than the water can go down.
Yeah, okay. So that's different. Yeah, I think that's a little bit a mystery, because I heard in California, it takes about 30 or 40 years for the nitrate in the surface water reach to the groundwater. So here,
it depends what is in between, right? And how do they know it takes that long? They also, I mean, you can look actually at the nitrate when it gets the groundwater. I think in China is full of nitrate, and that has to come from the surface. So, and it will be interesting to look in California too. What pollutes the groundwater? Do some tracer studies. But it is different. It can be different down there. The soil can be much tighter. We don't know. I mean, I don't know.
Yeah, I think when the pandemic is over, hopefully we can have some soil scientists to come to China, especially in the Yellow River Basin, because I think it's quite interesting. We have a really two different systems, right? In the upstream, you have the problem, the groundwater table rising. In the downstream, you have the decline of the groundwater table.
Yeah, and you can use that water by desalination. I don't know, that might be too expensive, but if the cities need more water, they need to desalinize the water. So
yeah, I think that could be a possibility, because the renewable energy, the solar and the wind, now they can get electricity cheaper, and if the people don't use that electricity, the electricity will be wasted in the grid, because the wind level stops blowing. So it's possible to use that wind energy to do a desal and to get some clean water, right?
Yeah, I think so. I don't know.
Yeah.
All right.
Yeah, but Professor Steenhouse, maybe I can ask question from because just like we just mentioned in the northern China, especially in the eastern side in the Yellow River, the basin, the lowest plateau. I think you probably know that, right? 就是how to say lowest plateau 黄土高原.
Oh, okay. Laos.
Okay.
Yeah.
So that area, like used to be lots of like the erosion, but now, like because China planted lots of trees, so recently, like less sediment, right, in the Yellow River, especially in the, like the south part of the Yellow River.
Could be very well. I did not know that, but that should be the same process. Runoff get usually generated by saturation excess and not by infiltration excess.
Okay.
Unlike what we learned in high school, but
So Tamo, you think even in some places in the Laos Plateau, the soil depths can be like a 30, 40 meter deep or 100 meter deep, that topsoil. So even in that case, in the saturation excess and runoff can still happen.
I mean, if you have a flat plain, right, then the water will build up. I mean, I don't know. I really don't know. But the picture I showed, I don't know where that was, but that was clearly that 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 was in the bottomland.
Mm-hmm.
The grass was green, so there was water. But you can have, but the banks were steep, so it was. I think it was a drier area.
Mm-hmm.
But I don't know in the dry area, but I suspect also in the dry area that the soil saturates, and after the gullies form, the soils desaturate. But I mean, we need to do more research. I mean, I don't know. It is, but I know that you find always these huge gullies in flatland. That is what, and the water cannot. There is not enough water to do it by itself. There needs to be
Right.
some other force.
Yeah.
Mhm. Yeah. All right. Okay. So I think it's time just it's maybe probably run out of time. So thank you again.
Okay,
Thank you for your support. And yeah, maybe in the after the pandemic, we can invite you in China to do some more research.
I don't know. if I outlive this, if I outlive the pandemic, but
Okay.
we'll take a while before the world is normal and we can travel without problems again.
Yeah.
Right. We'll see. Okay, thank you very much. Thanks again. And thank you for your support.
Okay, thank you.
Okay, bye. Okay, bye.
Tomo.
Bye.
Bye-bye.
Bye. See you.
Bye.
Mhm.